Okay, hello again. We continue from the place that we stop. Now I will talk about a couple of variants of statistical convergence. Uh, okay, one of them is said to be lambda statistical convergence. In other words, voilà point statistical convergence. Let lambda n be a non-decreasing sequences of positive numbers tending to infinity, such that the the difference of lambda n Artvir and lambda n plus 1 and lambda n is not greater than 1, and the first term of the sequence is 1. So lambda is a sequence of numbers that is not decreasing and going to infinity, such that this inequality hold. The generalized de la Voilà point mean is defined by this summation, where in is this interval. So uh, we sum xk's on the interval of in, which is determined by lambda n. If lambda n x sequence converge to L within ordinary sense, then we say that x is voilà point lambda summable to L. As you can easily see, if we take lambda n as n, then this summability reduces Cesaro summability. Yeah, so this mean, this generalized mean, can be considered as an extension of Cesaro mean of sequences. So now we can define a generalization of statistical convergence in regard with these lambda n sequences. Okay. A sequence xk is called to be lambda statistically convergent to number L if for each epsilon positive such that xk minus L greater than epsilon has a zero limit. So as you can see, we replaced k less than or equal to n and n with the interval in and lambda n respectively in the definition of statistical convergence. That's why we call this method to be lambda statistical convergence. And we write this by S lambda limit of xk equals L. Yes. Okay. We need to remark a couple of points here. If lambda n equals n for each n, then lambda statistical convergence coincide with statistical convergence. And secondly, lambda statistical convergence can be expressed by uh, by a matrix method in the following way. Let A and K as an infinite series be defined by one over lambda n if K is in In, otherwise it is 0. So this is the infinite matrix that gives us the concept of lambda statistical convergence. And we will define a generalization of strongly Cesaro convergence by lambda sense. Let lambda and be given as above. The sequence xk be is called to be strongly we lambda summable to L if limit of 1 over lambda n times finite summation equals 0. So if this limit is equals 0, then we say that x is strongly lambda summable to the number L. So we can think of the theorem that connects strongly lambda summability and lambda statistical convergence. if we lambda limit x equals L, then S lambda limit of x equals L. I mean, this statement expresses that strongly lambda summability implies lambda statistical convergence, preserving the limit. If x is in L infinity, that is, x is a bounded sequence, and S lambda limit of x k equals L, then the converse of the first statement holds. And lastly, the intersection of S lambda and L infinity equals the set of all strongly lambda summable sequences and bounded sequences. So this, the proof of this theorem is just an extension of the usual sense that Connor proved, that we talked about before. So we are gonna leave it without proving. So this theorem underlines the relationship between usual statistical convergence and lambda statistical convergence. Lambda statistical convergence is included by statistical convergence for all lambda equals lambda n, since lambda n over n is bounded by 1. And secondly, the converse of the first inclusion holds if and only if the limit inferior of lambda n over n is positive. Okay, I guess I believe this is enough for the concept of lambda statistical convergence. Now I'm gonna talk about another generalization of statistical convergence, which is called deferred statistical convergence. So let xk be any sequence and Pn and Qn be sequences of non-negative integers such that Pn is less than Qn for all n, and Qn tends to infinity as n tends to infinity. And mostly we call this duo deferred sequences, the deferred duo. Then dpq mean of sequence x is defined to be this ratio. Xk is called deferred Cesaro mean of x. This definition was given by Agnew in 1932. This generalized mean is an extension of Cesaro mean of sequences. So it satisfies all properties of Cesaro mean, but additionally it has some other properties that Cesaro mean do not meet. So now we are going to define another extension of strongly Cesaro convergence. A sequence xk is called deferred strongly summable to L by DOPQ if limit n goes to infinity of 1 over Qn minus Pn times Pn plus 1 to Qn xk minus L is 0. So as we can remember from here, this is the extension of the concept of strongly Cesaro summability under the idea of lambda sequences. And this one, another extension of the original concept of strongly Cesaro summability under the deferred duo sequences. And this is written by dpq limit xk equals L. So now we are going to extend the idea of statistical convergence to the concept of deferred statistical convergence. We say that a sequence xk is deferred statistically convergent to L if for each epsilon positive this limit equals 0. So as we can see again, from this definition, this is another generalization of statistical convergence. In this part, we talked about lambda statistical convergence by dividing this number by lambda n and selecting k's from in intervals. But here we slightly change the content by the deferred duo. Here we select k's from between Pn and Qn that holding the same inequality, see, and divide it by the distance of interval. So if this limit is 0, then we say that xk is deferred is statistically convergent to the number L. So we can easily say that if Qn equals n and Pn equals 0, then deferred statistical convergence is statistical convergence. There is a pretty distinguished difference between these two concepts. When we think about these intervals, because of the natural way of definition of lambda n, each interval is distinct from others. These ones, because the natural way of lambda n's. But when it comes to deferred sequences, since the conditions is not that strict, we can run into very different types of intervals. Some intervals can include other ones for some particular n's in some cases, but for some other PQ duos, we can see that all intervals created by Qn and Pn are disjoint. So this is an important distinction between these two methods. So between the relationship between deferred statistical convergence and the deferred statistical convergence and strongly deferred statistical summability can be given in this theorem. If dpq limit of xk is equal L, I mean if xk is strongly deferred summable to the number L, then it is deferred statistically convergent to the same number. But though the converse is not true in general. Let me give you an example of it. Let xk be defined by where m0 is a fixed natural number. So if k is between these two number, where this denotes the integral part of square root of qn, then xk is k square. Otherwise, it is 0. So then xk is deferred statistically convergent to 0, but it is not deferred strongly summable to 0. So if a sequence is bounded and deferred is statistically convergent, then the converse of the theorem become true. If x is bounded and it is deferred statistically convergent to L, then deferred PQ limit of xk is preserved with the same limit. So another characterization between statistical convergence and deferred statistical convergence can be expressed by the following. So here we talked about deferred. We talked about the relationship between deferred statistical convergence and deferred strong Cesaro summability of sequences. but one can think of what is the relationship between statistical convergence sequence and deferred statistical convergence of the same sequence. So this theorem discusses this problem. If the sequence Pn over Qn minus Pn is bounded, if this sequence of ratios is bounded, then statistical limit of xk, if it exists, then it implies that deferred statistical limit of xk equals L. So it is a pretty straightforward, it has a pretty clear proof. I will just give it briefly. For each epsilon positive and for all natural numbers, we can verify that this coming inequality is true. So this equals to 1 minus Pn over Qn minus Pn times the same ratio so taken limit, we see that this ratio is an convergent sequence to 0. So because we know that Pn over Qn minus Pn is a bounded sequence, so this number is less than or equal to a fixed number independent of n. So if we take a limit as n tends to infinity, we prove that deferred statistical limit of xk equals L. Okay. Okay, another important variant of statistical convergence was given by Aispuru and others in 2014. statistical convergence by a modulus function. First, we need to recall what a modulus function is. A modulus function, for short, modulus for short, is a function holding is a function f from positive real numbers into itself, holding the following conditions. First, f of x equals 0 if and only if x equals 0. And second, f is sub-additive. In other words, f of x plus y cannot be greater than f of x plus f of y. Third, f is increasing. And fourth, says that f is continuous from the right at 0. So any real defined and real valued function will be called a modulus function if it holds those conditions. So a couple of modulus functions can be given as follows. X over 1 plus x to the power t, where t is between 0 and 1. And h of x can be given as natural logarithm of x plus 1. So natural log x plus 1 are some examples of modulus functions. As you can see, there are some modulus functions that are bounded and others that are unbounded. For the sake of the definitions, we prefer unbounded ones over bounded ones. Okay. Before arriving at the formal definition of statistical convergence by a modulus function, we better to talk and discuss the concept of uh, density by a modulus function, which was given by Aispro and others. Let f be an unbounded modulus the f density of a subset of natural numbers is defined by lambda f of cap A as the limit of this ratio. If the limit exists where A sub n is equal to the numbers of the elements of A not exceeding the number n. So we can actually we can understand why it makes sense to select unbounded modulus functions over bounded ones from this definition. If sorry, I forgot to put here this. If we had chosen bounded ones, then this number will be less than or equal to a fixed number, right? Then if we take the limit, since fn tends to infinity, the limit would be 0 for any subsets of natural numbers. That would mean that every subset of natural numbers, regardless of being finite or infinite, has 0 f density, which is not interesting at all. So we are interested in having some subsets of natural numbers with 0 f density and the ones with non-zero f density. So so by this definition, now we can talk about statistical convergence by a modulus function. Let xk be a sequence and L be a real number. If for each epsilon positive 0, the f density of this set is 0, that is, this limit is 0, then x is said to be f statistically convergent, to the number L, and this is written by f statistical limit of xk equals L. So since all finite sets has 0 f density, we can easily say that every convergent sequence with usual sense is f statistical convergent to the same limit for any modulus function. I will share an important remark about the concept of f density, which is crucial for the theory, for this theory. For natural density, it is obvious that density of A equals 1 minus density of complement of A in natural numbers whenever one side exists. However, when it comes to F density, things is different. However, for some unbounded modulus functions, this is not the case. Let the density of A by a modulus function f be 0. Then the inequality f of n less than or equal to f of cardinality of an plus f of cardinality of the complement of A n holds for all n from natural numbers. Then we can write that 1 is less than or equal to this summation. And this summation is less than or equal to f of an over f of n plus 1. So if we take the limit here, we can write taking limit as n tends to infinity, we see that we get the f density of the complement of A is 1. So if a set of natural numbers has 0 f density, we can say that the complement of this aforementioned set has 1 f density. But the expected converse of this property does not hold for unbounded modulus functions. However, the converse need not hold in general. This is an example explaining this situation. Let f be natural log function of ln x plus 1. Then the set of all even numbers and set of all odd numbers have density f density 1. As you can see, even though these sets are complement of each other in natural numbers, it both has f density 1 when f, the modulus function, is taken as ln x plus 1. So now we are gonna talk about an proposition relating the relationship between natural density and F density. If the density of A with respect to modulus function is 0, then the natural density of it is also 0. So indeed, if equals 0, then for each p from natural numbers, there exists and not such that if n is less than or equal to n naught, we have the following inequality. Over p, and we use the sub-additivity of modulus function. By this, we can write that this ratio is less than or equal to 1 over p times f 1 over p times n, which equals f of n over p. So since holds, since f is increasing, we write that for all n greater than n naught, a n, the cardinality of a n over n is less than or equal to 1 over p, which yields that the natural density of A equals 0. So by this fact, we have three main corollaries, which is crucial to the theory of statistical convergence by a modulus function. First, F statistical convergence implies statistical convergence for any unbounded modulus function. Second, the F statistical limit of a sequence is unique. This is so clear. And lastly, the statistical limit of a function with different modulus functions is compatible. That is, if f statistical limit of xk equals L1, and if g statistical limit of xk equals L2, then L1 has to equal L2. So even though this fact is true, I mean, F statistical convergence implies statistical convergence. The converse of this result is not true in general. So in 2019, Professor Fernando and others gave a very productive characterization explaining what type of modulus functions hold the converse is true. To do this, we need a definition for some particular group of modulus functions. A modulus f is said to be compatible if for any epsilon positive there exists delta positive and a natural number n naught dependent by epsilon such that f of n times delta over f of n less than epsilon for all n greater than n0. So if a modulus function holds this property, then we say that it is compatible. Let me give you a couple of modulus functions that some are compatible and other not compatible. Fx x to the power p plus x to the power q with 0 less than p and q less than or equal to 1. G of x equal x to the power p plus ln x plus 1, and h of x h of x x plus x over x plus 1 are all compatible, whereas f of x, which is defined by natural log of x, is not compatible. So concept, we say that if f is compatible, then as t limit xk, I mean, if the sequence x is statistically convergent to L, then it is true that f statistical limit of xk equals L. So I guess this is a good place to stop here. I would like to hear your views or your questions if you have one. Yeah. 2 and 3? Okay. I mean, 2 says that if a sequence has f is statistical limit, it must be unique. And this one says that let us have two different type of modulus functions, and let x be, the sequence x be statistically convergent by these two different modulus, then the two limit has to be equal. This is called to be comparable. I mean, the consistency of the convergence. They cannot converge different numbers even though modulus functions are different. It comes from, actually it comes from the first one, because if this is true, and if we say that f is statistical limit of x is L, then since f is statistical convergence implies statistical convergence, then the limit of the sequence under modulus function has to be the limit of sequence under statistical sense, which is unique for Hausdorff metric spaces. I mean, this fact actually comes from the fact that we are working on Hausdorff spaces. Yeah, because this is the same thing with the usual sense, right? If a sequence is convergent with ordinary sense, then it has just one unique limit. And this is because of the fact that real numbers is a particular example of Hausdorff space concept. So this is also coming from this fact. If we deal with broader spaces, we gotta be careful with such properties equivalent to this property. Yeah.